Alright, so last time we began with an introduction to classical machine learning, and then we started to briefly discuss how quantum machine learning could make use of quantum algorithms for linear algebra and sort of pitfalls of that, or you need to read the fine print. Many of these algorithms require what's called a quantum random access memory, which we don't know how to do today. So today the plan is that we'll take a closer look at a particular machine learning problem, support vector machines. First we need to understand the classical problem, and so how it's solved classically, and then we'll look at an overview at least of how you can solve it with some quantum algorithms. It's a bit too complicated to go into all the details. We would need more than one lecture, but I hope you can see sort of how you use these different quantum algorithms. And then we'll sort of, as a bonus, we can see briefly how we can do some related or similar machine learning problems also with some quantum algorithms, if we have the time. And then the idea is that for next lecture we'll look at more quantum versions of neural networks. So let's see, quantum support machines. So what's a support vector machine? Does anyone know? More than care, because I know you know.
A classifier?
Classifier? Okay. So you can look at it like this. Let's say we have some data. Maybe some data points that are classified, labeled already as circles. And then we have some other data points that are crosses. So this is labeled data that we already have. We have data of the form some x, j, y, j, where x is then a vector. There can be more than 2 dimensions to it. And then y is labeled. So y, j basically is either -1 or +1, if it's one of these 2 classes. Now we have this data and we want to say sort of where's the dividing line between these 2 classes. And we want to find this because later we will be given new data that is not labeled, and then we want to be able to sort that data by just saying which side of the line is it. And then it's that class or that class. So you can sort of see that there should be here some dividing line. If it's tilted too much that way, it will be sort of too close here. And so this is some separating hyperplane.
What's hyper?
If it's more than 2 dimensions, so if this is in many dimensions, then this is not a line anymore, but it's some higher dimensional object. It's a hyperplane. Then you can sort of see there will be, at least in this simple example, there is some data point here in this class that's closest, and there's some data point here that's closest. And that sort of defines this optimal hyperplane. We want to find this hyperplane to be as far away as possible from this closest point, and it should be as far away as possible from that closest point from the other class. And it should be right in between these 2 points, right? Because then it's the optimal separation. Now, the equation for such a hyperplane can be written as some vector w, which specifies the plane, and then times x is that coordinate, minus some offset b. Then these 2 adjacent planes that go through the closest points, they will be one, and this one will be minus 1. So the distance between these 2 planes is 2 divided by length of this vector w. This parameter b tells you basically what the offset is from this plane to the origin. So, okay, the problem is to find this plane. Why is this called support vector machines? It's called that way because basically these 2 closest points in the classes, they are called support vectors. They are the ones that help to define this plane. Now, so the task is find the optimal plane. And you can formulate that as a minimization problem under constraint. So you want to basically minimize length of this w, or equivalently, usually you write it as the dot product in this cell. Subject to this constraint that yj, I use j there, right? Yj times So we saw that these planes given by this equation, it's -1 or +1. If you're further away, this will be larger than 1 or smaller than -1. So if we then multiply with a label yj, which is -1 or 1, so it will be, these are labeled -1, these are labeled +1, then that product always being larger than or equal to 1 is the same as saying that all points are outside these two lines. And then you minimize W such that this distance between these two planes here, 2 over W, becomes as large as possible. Yes?
But that constraint's not always, I mean, it won't always be satisfied unless there's a gap between the two data sets, right?
Yes. So I'm sweeping, like in a more real world situation, it could be that you have some misclassification or there isn't a clear gap like this. You can sort of add that to the formulation, slightly change the minimization of constraints here.
Instead of for RJ, you put something.
You minimize this, and then you have plus a term that counts the error or misclassifications with some, you change the cost function a little. It's not important for our discussion today, but essentially the algorithms and everything, they proceed as what we will see here. Yeah, you can add this thing that it's not fully separate.
Does it need to be a line or plain out, right?
That's the other thing that I'll come to that later. But yes, you can have some more complicated separating function. Okay, so how do we solve this minimization?
Gradients.
Gradient. Maybe. Yeah, I think you can do that after some rewriting. We will use Lagrange multipliers. Which is a normal way to take into account that you have constraints when you're doing minimization or maximization on the constraints. So you write down some Lagrangian here. The parameters you want to vary are W and B, right? And then we add vector of Lagrange multipliers, lambda, and we minimize this minus terms with these Lagrange multipliers. And here I'm again sweeping something under the rug, so usually this is how you would formulate it if you had some equality here in the constraint. Now we have an inequality, but it turns out to work time like this also with formulating it like this for the inequality instead. So now we look for stationary points of this Lagrangian. So we check where are all the partial derivatives zero. Partial derivatives with respect to lambda will basically give the constraints. Yeah, let's write it down. And it will actually work out like this in the end, that the lambdas that don't correspond to support vectors, I mean these closest points, they will end up being zero in the end. But we don't know yet which the support vectors are, so we can't say that. Then we have that partial derivative with respect to W. Which allows us to express the W in terms of y and x's. And that sort of, with that statement that in the end all the lambda j's that are not for support vectors will be zero, we can see that in the end we will be able to extract the W just from the support vectors, the x, j that correspond to the support vector. That will completely determine this W in the end.
Anton,
Yes.
what do you mean when you write the partial derivative of the Lagrangian with respect to W as a vector? Is it element Wj you take the part, or how do you?
No, I think
In the last line which
Yeah,
you
yeah.
just wrote.
I think it's with the whole. One could probably look closely at how exactly the definition is, but it sort of makes sense. Like you have this 1 over 2 W times W. You derive it, you get W. You differentiate, you get W. So we see that W will be determined by the support vector. And then finally we have derivative with respect to B. And then what one does now is to substitute this expression and this equality into the original Lagrangian. So we have, okay, this first term is just this, the 1 here, lambda j, right? And then we insert in this w both here and here, and we get that term, and from this that's a lambda j yj. Is 0. Yes, we have that this lambda j yj b term that becomes 0, because b is not j dependent. Okay, so we have that, and we have a constraint. Which is that this derivative with respect to b is 0. So now we've gotten rid of the w from the problem and the b. So we have now some problems then with lambdas. And then the y's and the x's are from the data. And what we now need to do is to find the lambda j's that maximize this expression. So we're at the saddle point of the Lagrangian where it's a minimum with respect to w and b, but a maximum with respect to lambda. Okay, this is a good point to address the question that Andreas had. So what if this separation isn't this neat hyperplane? What if, let's see, I can draw something. What if we have some data where actually the separation is some weird something very non-linear. What you do then is to basically transform your data into some space where you can separate them by hyperplane. So you use some function that maps the data in such a way that you can display it like that, separate it. So you transform all these vectors xj to what's called a feature space. And this transformation is usually then encoded as what's called a kernel or kernel function. Which replaces the dot product here. So this xi dot xj is replaced with some function k of xi xj. So in the case where you actually have nice data like this, you don't need any transformation, then k of xi xj is just equal to the dot product. But otherwise it's a more complicated expression. This is actually something that I think IBM did recently. As one possible application of quantum computing for machine learning was to use the quantum computer to somehow do some nonlinear mapping that realize such a kernel function. Okay, let's see, what should we erase? Yes. It's nice to have the picture, and it's nice to have that new problem there. That expression there with the lambdas is sometimes called the dual formulation of the support vector machine problem. Now, there's still some work to be done from here, and it's too much to go through the details there. So basically you can show that that problem of maximizing that Lagrangian under those constraints, you can transform that to solving a system of linear equations. There are different ways to do this. You can do some gradient descent method, as Pontus was mentioning also. But this is the formulation that we need. We have a matrix times a vector. Which will be something on this form roughly. probably should redefine the lambda slightly to have that being that constraint, but okay.
Do we know B in the first place?
B, no. B is one of the parameters you're
Okay,
trying.
B and lambda is what we are trying to find.
Yes, B and lambda. So this is like AX
Yeah.
equals B in a linear system. So this K here has its elements Kij given by this kernel function. So once you finally boil it down to this formulation, you can solve it classically. So how long does that take? Well, we have m data points, and we have our vectors x are in some m-dimensional space, Rm. So then you can say that calculating one entry in this kernel matrix, because we first need to set up the system and we need to then calculate all the entries in this kernel matrix. Calculating one entry in K takes order of n time. So to set up this whole system, is calculating the whole K. We do it with m squared times m, because we have m squared entries in K. Okay, half of them are the same, but same dependence on m. Then solving this system of equation takes on the order of m cubed. Do matrix inversion, m by m matrix. That's roughly where you So the classical problem of support vector machines, to solve it takes at least order of m squared times n plus m. Questions? So this is our baseline. This is what we have to compete with when we now go on to look at the quantum algorithm. Can we do better with the quantum algorithm? And the answer is yes. Well, assuming that we have a quantum random access memory. but that you will see after the break. So we'll take a break and we'll reconvene in 15 minutes. Yeah, 10 past 2.